Good day to everyone. My name is John Kenneth Rosales and I'm going to discuss the mathematician in 19th century. The first mathematician in the 19th century is Carl Friedrich Gauss. He was born on April 1777 and he died February 23, 1855. He is a German mathematician and physicist who made a significant contribution to the many fields in mathematics and science. Carl Friedrich is a greatest mathematician since antiquity and he is the rank among history and most influential mathematician. At the age of 7, he proved some of the integers from 1 to 100 instantly by spotting that the sum was 50 pairs of a numbers each pair summing to 101. He was the father of fundamental theorem of algebra. In 1792, he discovered Booth's law, which is the binomial and the arithmetic geometric mean, as well as the law of quadratic reciprocity and the prime number theorem. And one of his most important discoveries, the construction of a regular heptadecagon by ruler and compass. In 1801, Disquisition Arithmeticae is one of the book published with a 7th section. Carl Friedrich studied a series introduction of the hypergeometric function and statistical estimator. In 1822, he won the Copenhagen University Prize with the idea of mapping one surface onto another so that the two are similar in their smallest parts, and he initiated the possible existence of the non-Euclidean geometry from the early 1800s. And lastly, he published many papers on different geometry. And a very brief history of Carl Friedrich Gauss.
Carl Friedrich Gauss was one of the most important mathematicians to exist in the 19th century. He is sometimes referred to as the greatest mathematician since antiquity, or Princeps Mathematicorum, which means the foremost of mathematicians. A glimpse into what he is notable for includes his contributions to the theory of magnetism, proving the fundamental theorem of algebra, deriving the function representation of the normal distribution, and being PhD advisor to Richard Dedekind and Bernard Riemann, who would themselves go on to be very influential mathematicians. Gauss was born Johann Carl Friedrich Gauss on April 30th, 1777, in the Duchy of Brunswick-Wolfenbüttel, now part of Lower Saxony, Germany. His parents were poor working-class citizens, and with his mother being illiterate, Gauss's date of birth was never recorded. She only knew he was born on a Wednesday, 8 days before the Feast of Ascension, which occurs 39 days after Easter. Gauss derived methods to compute the date of Easter in any year, and was able to then figure out his birth date. Gauss was known to be a child prodigy. There's many variations of the story, but the way it usually goes is that when Gauss first got to elementary school in 1784, the class was asked to find the sum of the integers from 1 to 100. Soon after the question was presented, Gauss provided the solution, having recognized that 100 times 101 divided by 2 would yield the result. With the support of his elementary school teacher, Gauss went on to attend senior secondary school in 1788, where he studied language. He drew quite a bit of attention for his intellectual abilities, including from the Duke of Brunswick. The Duke provided him funding to attend university, thus allowing Gauss to attend the Collegium Carolinum from 1792 to 1795, and the University of Göttingen from 1795 to 1798. 1796 was apparently quite the year for Gauss. He advanced modular arithmetic, which greatly simplified manipulations in number theory. He was the first to prove the quadratic reciprocity law, which allows mathematicians to determine the solvability of any quadratic equation in modular arithmetic. He discovered every positive integer is representable as a sum of, at most, 3 triangular numbers. And he showed that a regular polygon can be constructed via compass and straightedge, if the number of its sides is the product of distinct Fermat primes and a power of 2. Construction problems had occupied mathematicians since the ancient Greeks. So this construction discovery firmly turned Gauss towards a career in mathematics instead of studying language. In 1798, Gauss left the University of Göttingen without a degree. But he did complete his writing of a fundamental work in number theory, officially being published in 1801, titled Disquisitones Arithmeticae, or Arithmetical Investigations in English. This was a pivotal work as it consolidated number theory as a discipline and shaped the field as we know it today. After leaving the University of Göttingen, Gauss returned to Brunswick in 1799, finally receiving his degree. The Duke agreed to continue Gauss's funding, but requested that Gauss submit a doctoral dissertation to the University of Helmstedt. Gauss knew a professor there named Johann Friedrich Pfaff, which made it easier to get his dissertation through and ultimately get his PhD. The work that Gauss submitted provided the first proper proof of the fundamental theorem of algebra, formulated over the real line, as well as arguments against people's previous attempts at proving the result. Gauss actually proved the fundamental theorem of algebra 4 times in his lifetime. The first proof in 1799 was topological in nature and doesn't hold up to the rigor of today's standards. The second proof was published in 1816 and was influenced by the approach that was originally taken by Euler without assuming the existence of roots. This proof is both complete and correct, rigorous enough for today's standards. The third proof was published later in 1816, sharing the topological spirit of the first proof. His fourth and final proof was provided in 1849, 50 years after his first proof. The approach taken was similar to the first proof, simply extending the theorem to work for complex numbers. Things seemed to be going quite well for Gauss after returning to Brunswick, and he got married to Johanna Astaf on October 9, 1805. Sadly, the Duke of Brunswick died on November 10, 1806, about 2 months after Gauss and his wife had their first child, Joseph. Gauss ended up getting an offer to work as the director of the Astronomical Observatory at the University of Göttingen in 1807. It seemed this was the most appropriate move to make, especially after the Duke died. Aside from the Duke's death, more tragedy would strike Gauss upon his move to Göttingen. On April 14, 1808, Gauss's father died. This was about a month and a half after Gauss and his wife had their second child, Wilhelmina. On October 11, 1809, Johanna died, just 2 days after their 4-year anniversary and a month after giving birth to their third and final child, Louis. And on March 1, 1810, Louis died. Considering these terrible events, especially the death of Johanna, Gauss attained a depression that he'd be afflicted with for the remainder of his life. But he didn't let this affect his work, publishing his second book in 1809. This was a major 2-volume work on the motion of celestial bodies, titled Theory of the Motion of the Heavenly Bodies Surrounding the Sun in Conic Sections. Volume 1 discusses differential equations, conic sections, and elliptic orbits. Volume 2 showed how to estimate and then refine the estimation of a planet's orbit. Focusing heavily on astronomy until 1817, Gauss still found time to work on other things, such as general investigations of curved surfaces, which was a rigorous treatment of series and introduced the hypergeometric function, and determination of the accuracy of observations, which was a discussion of statistical estimators. In 1818, Gauss was asked to carry out a geodesic survey of the state of Hanover to link up with the existing Danish grid. This led Gauss to become heavily focused on the study of geodesy, which is the branch of mathematics dealing with the shape and area of the Earth or large portions of it throughout the 1820s. His work on the Danish grid project led him to creating the heliotrope, which worked by reflecting the sun's rays using a design of mirrors and a small telescope. Alas, the measurements ended up missing the mark, leaving Gauss to wonder what kind of mathematician he really was. Regardless of the geodesy hiccups, Gauss still pursued mathematical physics. In 1832, Gauss began working with Wilhelm Weber on the theory of terrestrial magnetism. The work Weber and Gauss did together led to the discovery of Kirchhoff's laws, and to the building of a primitive telegraph that could send messages a distance just shy of 1 mile. By 1840, Gauss had written 3 papers on terrestrial magnetism, all of which dealt with the current theories at the time, as well as absolute measure of magnetic force and an empirical definition of terrestrial magnetism. Gauss became kind of notorious for letting mathematical results ripen. It's claimed that if he had published all of the results that he'd let ripen, mathematics could have been 50 years ahead of what it currently is. A prime example of this ripening, which Gauss never actually published work for, is non-Euclidean geometry. His wondering of the existence of non-Euclidean geometry began in the early 1800s. He primarily corresponded with Farkas Bolyai on this matter, but expressed that he developed a non-Euclidean system for himself to tinker with in a letter written to Turinus in November of 1824. In 1831, Bolyai's son Janos had published work on non-Euclidean geometry, but Gauss's response was essentially that he derived this years earlier, being occupied with these thoughts for 30 to 35 years. Gauss would later express something similar in a letter to Schumacher in 1846, regarding a work published by Lobachevsky in 1840. So, even though Gauss probably didn't mean it to sound the way it did, he was essentially giving off the vibe that their results weren't that impressive since he'd already discovered them years ago, but just never published them. Returning to Gauss's personal life, Gauss got married to his previous wife's best friend, Mina Waldeck, on August 4th, 1810. This was about 5 months after the death of his son Louis, and given how depressed Gauss was over the death of Johanna, let alone all the other events that had unfolded up to that point, it is speculated this marriage was largely for convenience, despite having a marriage with Mina for about 21 years. Gauss had 3 children with Mina: Eugene, born in 1811, Wilhelm, born in 1813, and Teresa, born in 1816. Gauss wasn't very supportive of his children pursuing mathematics, for fear they could never live up to his quality of work, and thus tarnish the Gauss name. This presumably led Eugene and Wilhelm to immigrate to the United States, Eugene immigrating to Missouri in 1832, and Wilhelm following suit in 1837. They both independently became very wealthy entrepreneurs, so this move seemed to be quite successful. In the year following Teresa's birth, Gauss's mother moved in, as she was too ill to take care of herself. Mina and her family had been trying to persuade Gauss they should move to Berlin, as Gauss got an offer from the University of Berlin to work there. Gauss wasn't too keen on the change, and with his mother moving in, this seemed to be the nail in the coffin for any ideas for moving to Berlin. Gauss's mother lived with him and his family until she died in 1839. After Mina died on September 12, 1831, and Teresa becoming the caretaker of the household, she tended to her grandmother and then ultimately her father. As is quite clear, Gauss made incredible contributions to mathematics and mathematical physics, but he was also able to make incredible contributions to his pockets. From 1845 to about 1850-1851, Gauss worked on updating the Widows' Fund for the University of Göttingen. The experience he gained from this led him to make investments in bonds issued by private companies, which turned out to be incredibly successful. After this series of investments, Gauss began to focus almost primarily on mathematical physics, and he went on to do this until his death on February 23, 1855, fortunate enough to pass in his sleep. Well, there you have it. A very brief history on one of the most important mathematicians, if not the most important, of the 19th century. Thanks for watching, and long live Gauss.
The second mathematician in 19th century is Agustin Cauchy. He was born on August 21, 1789, and he died May 23, 1857. He is a French mathematician. In 1811, proved that the angles of the convex polyhedron are determined by its bases, and investigate symmetric function. In 1814, published the memoir of the definite integrals that later became the basis of his theory of the complex function. Agustin Cauchy was the first to make a rigorous study of the condition for the convergence of infinite series in addition to his rigorous definition of an integral. In 1829, defined for the first time in a complex function of a complex variable. Terms in mathematics bearing Cauchy's name. First, the Cauchy integral theorem. Second, the Cauchy-Kovalevskaya. And lastly, the Cauchy-Riemann equation in sequence. Cauchy integral theorem about line integrals from holomorphic function in the complex line. Essentially, it says that if two different paths connect the same of 2 points and a function of the holomorphic everywhere in between the two paths, then the two paths integral of function will be the same. Cauchy-Kovalevskaya theorem states that a partial differential equation involving a time derivative of order n, the solution is uniquely determined if time derivatives up to order n minus 1 of the dependent variable are specified as a single surface, provided the surface is a free surface. The Cauchy and Riemann equation and sequence consists of a system of two partial differential equations which, together with a certain continuity and differentiability criteria form a necessary and sufficient condition for a complex function to be a complex differentiable, that is homomorphic.
Hi, I'm Adelina, and together with Rebecca and Subin, we'll be talking about Augustin Louis Cauchy and what he did to be considered one of the most influential mathematicians of modern times. But first, a bit about the life of the man himself.
Augustin Louis Cauchy was born in Paris on the 21st of August 1789, 10 days after the fall of Bastille and the start of the French Revolution, to middle-class parents, Louis Francois and Marie Madeleine. Cauchy's father was a parliamentary lawyer, lieutenant of police, and an avid royalist. Sensing danger with the fall of Bastille, Cauchy's father decided to move the family to a town called Arcueil in the French countryside. It was there that Cauchy received a highly religious education from his mother and a classical education from his father until the family moved back to Paris when he was 11 years old. The French Revolution lasted for the first 10 years of Cauchy's life. By the year 1800, the French political situation had settled, and Cauchy's family felt safe enough to move back to Paris, where at the age of 18 he entered École Polytechnique, which at the time was considered one of the best schools in the world for young aspiring mathematicians. The teaching at the school was linked with research being conducted with the nation's leading mathematicians, and Cauchy attended courses by Lacroix, de Prony, Hachette, and his analysis tutor was Ampere. As well as attending this highly prestigious school, Cauchy's early life was influenced by the mathematicians Laplace and Lagrange, who were frequent visitors to his household. These famous mathematicians were highly influential at the time, and Lagrange in particular took a deep interest in Cauchy's mathematics education. As Laplace and Lagrange had predicted, Cauchy excelled at his mathematics school, and after graduating from the École Polytechnique in 1807, he entered the engineering school École des Ponts et Chaussées. After graduating, Cauchy became an engineer in Cherbourg, working on port facilities for Napoleon's English invasion fleet. While he was working as an engineer, he couldn't resist also conducting mathematical research and started proving theories about polyhedrons, symmetric functions, and determinants. Cauchy eventually decided to stop his work as an engineer and focus on his mathematical research after a bout of depression in 1812, where he decided to return to Paris. This decision proved extremely fruitful for Cauchy as he became a prolific research mathematician with a plethora of awards and titles. By 1818, he was married to his wife, Aloise de Burgh. He then had two daughters, Marie Françoise Alicia in 1819 and Marie Mathilde in 1823. Throughout his life, Cauchy baffled his contemporaries with his staunch evangelical Catholic faith. They could not believe that such a brilliant academic mind could hold such bigoted views when it came to religion. The Second French Revolution in 1830 sent King Charles X into exile, and the new king Louis Philippe demanding oaths of allegiance from French professors. Cauchy refused, having already sworn his allegiance to Charles, and was stripped of his honours. He then exiled himself to Switzerland, leaving his family in Paris. He was later allowed to return to Paris, where he worked as a lecturer. Cauchy died on the 23rd of May 1857. His last words are believed to be, "Men die, but their works endure."
Next, I'll talk about Cauchy's mathematical accomplishments. It's very unlikely you've never heard the name Cauchy before, given he has formulas named after him in everything from number theory to elasticity, algebra to hydrodynamics. His contributions to math and science certainly haven't gone unnoticed. However, it was his contributions to the development of calculus in his publication, Cours d'analyse, that he truly made his mark. While calculus had existed for over a century prior to Cauchy's birth, its foundations were still somewhat weak. Cauchy was one of the first people to help construct a more rigorous foundation that logically explained calculus. Cauchy is considered the first to define calculus in terms of limits and continuity, and also introduced the epsilon-delta notation used in calculus proofs and definitions today. A big contribution was his criterion for convergence. A Cauchy sequence is a sequence an where for all epsilon greater than 0 there exists a positive integer n, such that for all n and m greater than n, an minus am is less than epsilon. Since every convergent sequence is Cauchy, it provides a method of determining convergence without a limit. Cauchy is also considered by many to be the father of complex analysis. While the idea of complex numbers definitely didn't originate with Cauchy, he provided the first comprehensive theory of complex numbers, forming the foundations of the field. Most famously is his integral formula, where if f of z is an analytic function for a simply connected region in a complex plane, and if c is a closed contour in the region, then the contour integral f of z dz equals 0. When generalized, you get the residue theorem, 1 over 2 pi I times the contour integral of f of z dz equals the sum of the residues of f of z. This allows us to evaluate line integrals of analytic functions over closed curves.
I have researched about Cauchy's work with other mathematicians. One of the famous work is Integral Test for Convergence. This work is combined with Maclaurin, so it is called Maclaurin-Cauchy test as well. Most of the students must have learned this test in first year in University of Mathematics. This is when let the function f be continuous, non-negative, and monotone decreasing function, which is bounded from n to infinity, where n is a positive integer. Then the finite series an will converge if and only if the integral of the function from 1 to infinity converges. So conversely, if the integral of the function diverges, then the series diverges as well. Thanks to this discovery, we were able to find some harmonic series, such as 1 over n series, where n starts from 1 up to infinity diverges. This is an important discovery because the proof gives the lower and upper bound for finite series if the improper integral is finite. Another great contribution is Cauchy-Riemann equation. This discovery is used in complex analysis, which consists two partial differential equations, which are du over dx equals dv over dy, and du over dy equals negative dv over dx. In complex fields, u is a real part and v is an imaginary part which consist x and y. In order for the equation to work, both of the functions u and v should be continuous and differentiable. This is a condition for complex functions to be holomorphic, in other words, to be complex differentiable. This work has first noticed by D'Alembert in 1752, and Euler has connected this to analytic functions later in 1797. Then Cauchy used this equation to construct his theory about functions in 1814. Riemann wrote this equation in his thesis in 1851. It became Cauchy-Riemann's equation. We still use this test, shortened as CRE, in complex analysis to determine whether the complex field is holomorphic or not. In conclusion, Cauchy has contributed a lot of work in mathematics, and he has developed a lot of expansion in many aspects of mathematics. Thank you for listening.
The next mathematician is Nikolai Ivanovich Lobachevsky. He was born on December 1, 1793, and he died February 24, 1856. He is a Russian mathematician, and he studied geometry in which Euclid's postulate does not necessarily hold, and he worked on the development of non-Euclidean geometry and worked on hyperbolic geometry. In 1834, he found a method for the approximation of roots of algebraic equations.
Einstein wouldn't have created the theory of relativity without the work of mathematician Nikolai Lobachevsky. Lobachevsky entered the University of Kazan only at the second attempt, but at the age of 24, he became its professor and then the rector. He proved to be an excellent administrator. He rebuilt the university and saved many students during a cholera epidemic. But his main achievements were made in the field of science. Geometry of that time was based on the postulates of the ancient mathematician Euclid. One of them states that given any straight line and a point not on it, there exists one and only one straight line which passes through that point and never intersects the first line. Lobachevsky proved that the theory is valid only for ordinary space, but does not work in curved space. However, contrary to the myths, Lobachevsky did not argue that the parallel line may intersect. Lobachevsky's theory turned out to be too revolutionary. It took scholars 12 years to recognize it. But it was this theory that allowed Einstein to describe the curvature of space and time.
The next mathematician is Johann Peter Gustav Lejeune Dirichlet. He was born on February 18, 1805, and he died May 5, 1859. He is a German mathematician and began the golden age of mathematics in Berlin. In 1825, he became famous when he attacked Fermat's last theorem. Fermat's last theorem states, for n greater than 2, there are no zero integers x, y, and z such that x to the n plus y to the n equals z to the n. For n equals 5, then made a later contribution proving the n equals 14 case. As if n equals 5, then 1 of x, y, and z is even and 1 is divisible by 5. In 1828, he wrote papers on a condition for the convergence of trigonometric series and the use of series to represent arbitrary functions. In 1837, proved arithmetic progression with the first term co-prime the difference there are infinite many primes, and proposed the modern definition of a function if a variable y is so related to a variable x that whenever a numerical value is assigned to x, this is a rule according to which unique value of y is determined, then y is said to be a function of different independent variable x. In 1838 and 1839, he published two further papers on analytic number theory, introducing the Dirichlet series and the formula for the class number of quadratic form.
Actually, Fourier said that any signal can be expressed as a linear combination of complex exponential. However, he has not carried out the mathematical analysis for that. It is P.L. Dirichlet who has conducted the mathematical analysis and came with some conditions for the existence of Fourier series. So Dirichlet was a famous German mathematician, and he is famous for his contributions in Fourier series analysis. In 1989, he proposed the precise conditions under which the Fourier series exists for a periodic signal. So if the signal satisfies these conditions, then we can say that the Fourier series exists for that particular signal. For x of t equals its Fourier series representation, there are some conditions developed by Dirichlet, and these conditions are known as Dirichlet conditions. So Dirichlet shows that if x of t satisfied these conditions, its Fourier series is guaranteed to converge point-wise at all points where x of t is continuous. That is Dirichlet's main contribution. He has done this in 1829 after the death of Fourier. So now let us analyze the conditions one by one, and let us check whether there are some signal which does not obey this Dirichlet condition, so that there is no Fourier series exist for those signals.
And the fifth mathematician is Évariste Galois. He was born on October 25, 1811, and he died May 31, 1832. He is a French mathematician, and the contribution of Évariste Galois is the group theory. Group theory is a part of the higher algebra which provides a solution to the long-standing question of determining when an algebraic equation can be solved by radicals. In 1829, his first mathematics papers published on continued fraction, and he worked on a theory of elliptic function and abelian integral.
Évariste Galois was a brilliant French mathematician. His greatest contribution to maths was to show when an algebraic equation can be solved by radicals. In other words, a solution containing square roots, cube roots and so on, but no trigonometric or other non-algebraic functions. Sadly, his short life ended tragically, as we're going to find out. As a teenager, Galois' great ability to solve problems effortlessly in his head and write down results without filling in the detail of how he'd arrived at them exasperated his teachers and held him back academically. That didn't stop him from doing his own research, however, summarized in a handful of papers, some published posthumously, in which, while searching for solutions to polynomial equations of degree 5, he effectively founded the theory of groups. At the age of just 17, he began making fundamental discoveries in the theory of polynomials. He proved that there can be no general formula for solving quintic equations, those that include a term of x to the 5. The Norwegian Niels Abel had done this independently a few years earlier by a different method. Galois, though, proved the more general and powerful idea that there's no general algebraic method for solving polynomial equations of any degree greater than 4. Galois achieved this general proof by looking at whether or not the permutation group of its roots, now known as its Galois group, had a certain structure. He was the first to use the term group in its modern mathematical sense of a group of permutations, and his approach, now known as Galois theory, was adapted by later mathematicians to many other fields besides the theory of equations. Things began to go badly wrong for Galois in 1829, beginning with his father's death by suicide. The young man's political activities — he was a staunch Republican, prone to outspoken and hot-headed demonstrations — led to him being thrown into prison on a couple of occasions, though he continued doing maths while behind bars. Shortly after being released from his second spell in jail in 1832, he got involved in a duel, possibly over a woman, though the circumstances remain unclear, and it may possibly have been a trap laid for him by political opponents. In any event, Galois was shot in the abdomen during the contest and died the following day, aged just 20. So sure was he that he'd be killed, that he spent the night before writing down some of his most important mathematical ideas. These notes, together with a handful of unpublished papers, were discovered 14 years later by Joseph Liouville, the discoverer of transcendental numbers, who recognized Galois' previously unknown writings as works of genius and brought them to the attention of the world. Galois' great strength was his ability to leap ahead of others and break into new areas of maths without having to dwell too long on the intermediate steps. But being so far ahead of his time and lax in his proofs frustrated his contemporaries. It was only much later that the importance of his contributions was fully realized.